Mixtures of gases. We've talked a lot about the simple gas laws and the ideal gas law. And for the most part, we've talked about that as just being a single gas. But actually, many gas samples are mixtures of gases. The air in this room is an example. It's a mixture of different gases. This is the percent composition of dry air. And by dry air, we just mean air without humidity, without water in it. So by volume, air is 78% nitrogen, 21% oxygen. So those are the main gases in air. A little bit of argon, a little bit of carbon dioxide. It's a mixture. If we take a sample of air and measure the pressure, the volume, and the temperature, it behaves just like a sample of a pure gas, like it wasn't a mixture. And so we could calculate the total number of moles of molecules in this mixture of gases, even though they're different molecules. And that's because gases behave independently of each other. So in this room, there's nitrogen molecules and there's oxygen molecules. They are just doing their own thing. They're not changing their behavior based on the fact that there's other kinds of molecules around. They just behave independently. So the two gases, nitrogen and oxygen, both behaving independently, like the other gas isn't there, they are each going to exert a pressure on whatever container they are in. And that's called a partial pressure when it's the pressure of one gas in a mixture. Because it's not the total pressure of the gas sample, it's just the pressure from an individual gas, so it's part of it. So we could calculate the partial pressure of, we'll call it gas N, in a mixture, using the ideal gas law. So we rearrange the ideal gas law, we get pressure equals the number of moles of N times RT over V. Okay, we've done some problems like that. A guy named John Dalton, also known for Dalton's atomic theory, has Dalton's law of partial pressures. And this just says that the total pressure of a mixture of gases is the sum of each of the individual pressures. So we could think of it this way. Think of a box of fruit. I live in Reedley. There's a lot of fruit in Reedley. There's nuts too, but you know, California's the land of the fruit and the nuts. So let's say we've got 1, 2, 3, 4, 5 oranges, and 1, 2, 3 lemons in this box. And the oranges weigh, here's lemons, here's oranges. Those aren't very oranges, sorry about that. Let's say the lemons weigh, these would be big lemons, 1 pound, and the oranges weigh 2 pounds, just to make the math easy. What's the total mass of fruit in the box? Well, you've got 5 oranges, they're each 2 pounds, right? So that's 10 pounds of oranges and 3 pounds of lemons. Would the mass of the oranges change if you took the lemons out? No. The mass of the oranges is independent of what else is in there. Their mass affects the total mass. It's the same idea with partial pressures of gases. The pressure exerted by one gas doesn't change when you take the other gas out. The mass of oranges doesn't change if I take the lemons out. They're independent. And the total pressure is just the sum of the pressure exerted by each gas. Any questions? Yes?
And so from that you can deduce like percentage?
Yeah, we can get percentages from that, and I'll get to that in a minute. So if you don't like math derivations, just, think about puppies or something for a while. So here we have Dalton's law, which says that the total pressure is equal to the pressure of each individual gas. And we just showed how the pressure of one gas is equal to the number of moles of that gas times RT over V, T being the temperature, V being the volume. So the pressure from gas B is the moles of B plus RT over V times RT over V plus et cetera, et cetera. Because all of these gases are in the same container, they're at the same temperature, they're at the same volume. So RT over V is the same for all of them. We can factor that out. And then we get the total pressure is equal to the total number of moles times RT over V. So the ideal gas law works whether you're looking at individual gases or at a mixture of gases. If you're using a mixture, you could get the total number of moles of molecules or atoms of the gas. Any questions? So let's talk about mole fraction. And before I do that, let's talk about what did I say was the general expression for a percentage? Something over something. The part over the whole, right? It's the part that you're interested in divided by the whole thing times 100. If we leave off the times 100, it's a fraction, not a percentage. This mole fraction is like a mole percentage. We just left the 100 off. It's the part we're interested in, the number of moles of gas A divided by the total number of moles of gas. So it's like the percentage divided by 100. So if we're looking at the ratio of the partial pressure of A to the total pressure, I guess you could call that a pressure fraction, but we don't. The pressure of A equals this. The total pressure equals this, and the RTVs cancel out. And so the ratio of the pressures is equal to the ratio of the moles. The pressure depends on the number of molecules. So bottom line is over here. The partial pressure of gas A equals the mole fraction of gas A times the total pressure. That's a very useful equation you should know. And this is another one. Mole fraction, that funky looking X is the Greek letter chi. Chi equals the moles of A over the total number of moles. Any questions? So that equation is just saying that the partial pressure of a component in a gas mixture is its mole fraction multiplied by the total pressure. So it's similar to the apples and oranges, or no, it was lemons and oranges. Lemons and oranges. We usually think in terms of percentages. Let's just do that. The percentage of mass of lemons is the fraction of mass of lemons times the total, right? So for gases, we've got the mole fraction is the percent by volume divided by 100%. So nitrogen has a 78% composition of air. Actually, air has a 78% composition of nitrogen. But anyway, find the total partial pressure of nitrogen. Well, we're going to take 78% and convert it to a decimal, a fraction. It's just 0.78. So it's 0.78 times 1 atmosphere. So the pressure from nitrogen is 0.78 atmospheres. It makes sense. If nitrogen is 78% of the gas, it exerts 78% of the pressure. That makes sense? Let's do an example. To prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. A chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15 grams of neon, and 35 grams of krypton in a piston cylinder assembly at STP. Calculate the partial pressure of each gas. Most of you, I think, having read that are going to think, how does that relate to what we just talked about? Bless you. Well, partial pressure of each gas, let's pull this apart and think about it. We've got a mixture of gases, right? So I'm just going to kind of write some stuff down. So the total pressure of this gas mixture is the partial pressure from helium plus the partial pressure from neon plus the partial pressure from krypton. What is the total pressure in terms of like a number? How many atmospheres? What does at STP mean? Standard temperature and pressure. Standard pressure is 1 atmosphere. So this is equal to 1 atmosphere. May or may not be relevant, but there it is. So we want to know these individual pressures. 1, 2, 3. We've got 3 of them. We're trying to find 3 things. This is a great equation. We know they all add up to 1, but there's 3 things, so we can't just find them. We'll deal with some simpler ones where we know all but one of these, and then you can just do some simple subtracting and find the answer. Well, maybe we need some more information or another relationship. So if we go back over here, this relates the partial pressure of a gas to the total pressure of a gas mixture, and the relating factor here is the mole fraction. Could we calculate the mole fraction given the masses? Yes, yes we could. So the mole fraction, say, of helium is going to equal the moles of helium divided by the total number of moles. Could we figure out the moles of helium? Sure, we're given a mass. We have a periodic table. We can convert that to moles. Could we figure out the total number of moles? Yeah, it's going to be a little tedious maybe, but we can convert this to moles and that to moles and that to moles and add them together. Total number of moles. And if we have that, then the partial pressure of helium is going to equal the mole fraction of helium times the total pressure. We know what the total pressure is. It's 1 atmosphere. So we need to calculate mole fractions. So 5.50 grams of helium. To get that to moles, we're going to use the molar mass, 4.003 grams per mole. Well, that's not right. Try that again. 5.5 divided by 4.003. This number has 3 significant figures. So I'm going to try to be a good example and carry extras, the 2 extras. So there's our 3. That's the moles of helium. We need moles of neon. 15 grams of neon times 1 mole over 20.18 grams. 15 divided by 20.18, 0.743, 31 moles of neon. It's really hard to fit all of this on this little screen. 35 grams of krypton. Always makes me think of Superman. So that was kryptonite. 83.80. So 35 divided by 83.8. 0.41866 moles of krypton. So what's the total number of moles? It's those three added together, right? 1.3740 plus 0.74331 plus 0.41866 equals 2.53597 is what my calculator shows me. How many significant figures does that sum have? 3. It has 3 because rules of sig figs for adding says that you look at the number with the fewest decimal places. This has 2 decimal places, this has 3, this has 3, so our answer should be rounded to the second decimal place. So now we can calculate the mole fraction of helium. It's the moles of helium divided by the total number of moles What happens to the units when I do that division? What units does the mole fraction have? It cancels, but it's not a percentage. It's actually unitless. It would be a percentage if we multiplied by 100. As it is, there's no unit. Thank you for volunteering an answer. It was very close. Moles cancel, right? So there's my mole fraction for helium. So I'm going to plug it into this equation. So my mole fraction, 0.5418, 0, times the total pressure, which was 1 atm. When we say something is at STP, you can take that as exact. So this little equation is not really necessary here, but there we go. So that is the partial pressure of helium. Any questions?
So now you have to find the partial pressure for the other two.
Now we have to find the partial pressure of the other two. Yeah. It's like, oh man. We need some space. Well, to find the mole fraction of, the partial pressure of neon, you can see that this is getting a little bit redundant and tedious, right? So the mole fraction of neon equals, the partial pressure of neon equals the mole fraction of neon. Well, this is the mole fraction of neon. So how about we just kind of expand that equation and say, okay, well, it's the number of moles of neon divided by the total number of moles times the total pressure. And save a little bit of writing that way. Moles of neon is 0.74331. Moles divided by the total number of moles, 2.53597. And again, those mole units are going to cancel out, and we're multiplying by exactly 1 atmosphere. Point 74331 divided by 2.53597 equals times 1. 0.29311 0.293 atmospheres. So that is the partial pressure for the neon. Any questions? There's 2 different ways we could calculate the partial pressure for the krypton. We could do the same equation using the number of moles of krypton, Or we could use this equation and say, well, all of these add up to exactly 1 atmosphere. If I subtract the partial pressures of the other two from 1, what's left must be the partial pressure of Krypton. Which one should we do? Subtracting? So the partial pressure of Krypton then is going to equal the total pressure, that 1 atmosphere, minus the partial pressure of helium, minus the partial pressure of neon. So we've got 1 ATM minus 0.29311 ATM minus 0.5418 ATM. My calculator gives me 0.16509. Where would the last significant figure be in that number? Be in the third decimal place. It'd be right here. And so we call that 0.165 atmosphere. Any questions? I think the biggest question is, why would you ever need to do that? And my best answer for that is it might be on a test. Could happen. Let's do another example. A sample of hydrogen gas is mixed with water vapor. The mixture has a total pressure of 755 torr, and the vapor pressure has a partial pressure of 24 torr. What amount in moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 Kelvin? Well, let's pull the numbers out and identify what they are. That's always a good starting point. So we've got some pressures listed here. We've got 755 torr, and we've got 24 torr. The 755, it says that's a total pressure, so I'm going to call that PT. And the water vapor, vapor is just another word for gas. Water in the gas state has a partial pressure of 24 torr. So that's a partial pressure of water. This is a gas mixture. What's the other gas? Not oxygen. Hydrogen. So we've got hydrogen gas mixed with water vapor. So the total pressure equals the pressure of the hydrogen gas plus the pressure of the water vapor. Could we figure out what the pressure of the hydrogen is? Yeah, we don't have to do that whole mole fraction thing here because this equation, there's only 3 variables because there's 2 gases and a total pressure. We know what 2 of those are, we can find the third one. So the total pressure minus the water vapor pressure is going to give us the pressure of the hydrogen gas. So that's the partial pressure of hydrogen. And then we've got 1.55 liters. That sounds like a volume. And 298 Kelvin, that's a temperature. What are they asking us for? Moles. Moles of hydrogen. So what equation do we use? PV equals nRT. So the moles of hydrogen are going to be equal to PV over RT. That's the pressure of the hydrogen times the volume divided by the ideal gas constant times the temperature. The volume and the temperature are the same for both of the gases, the water and the hydrogen. But when we do this calculation, if we want moles of hydrogen, we have to use the pressure of the hydrogen, because the water vapor is in there exerting its own pressure from its own number of molecules. So you have to watch out when you're dealing with these mixtures. So 731 torr, is that going to work in our ideal gas law? No, we got to convert it. We need it to be in atmospheres. So we'll convert that 731 divided by 760. 0.96184 atmospheres. So pressure 0.96184 atmospheres. The volume was given to us in liters. That's nice because we need liters. Divided by the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin, times the temperature. It's already in Kelvin. When we check our units, atmospheres cancel, liters cancel, Kelvins cancel. The unit that we're left with here is 1 over moles. If you flip a fraction upside down twice, then it's right side up. So that's just moles. So 0.96184 times 1.55 divided by 0.08206 divided by 298. Zero 0.0609, there's my 3 sig figs, 66 moles. So I'll round that to 0.0610 moles of hydrogen gas. Any questions? Sounds like no questions. Mixtures of gases are very significant if you're doing any deep sea diving. I've never done this. I have no desire to do it, but I think it's kind of interesting. When you breathe compressed air, the pressure of oxygen that you're breathing is higher than what we have breathing just regular air at sea level. One thing I hope I'm getting across to you is that everything that is matter, that has volume and mass, is actually a chemical, right? It's composed of elements, so technically it's a chemical. And all chemicals are toxic at some level. And so, we have this, idea that, oh, well, if it's natural, it's safe. Well, no, not necessarily. There's some very toxic natural things. And even things like oxygen that we need to live. Oxygen, how long can you live without oxygen? I think the record's like 17 minutes or something, and that was with a lot of training, right? We have to have oxygen, or we'll die. But if we get too much oxygen, we will also die. Right? So it's like moderation in all things. The trick is just to know what's that safe range to be in. If you've got oxygen partial pressures above 1.4 atmospheres, then you get into oxygen toxicity. When your oxygen pressure gets too low, down here around 0.1, you've got hypoxia, which means low oxygen, and that can also be fatal. So when you're breathing compressed air, I didn't mean to do that. Remember that the partial pressure, let's say, of oxygen equals the mole fraction of oxygen times the total pressure. So if I take air, which is 21% oxygen, or a mole fraction of 0.21, and I increase the pressure, what does that do to the partial pressure of oxygen? it makes it go up. So at the surface, we've got partial pressure of oxygen of 0.21. That's ideal. If you go 30 meters below the surface of the water, in order to be able to breathe, you're going to need your pressure regulator set up to 4 atmospheres. Otherwise, you're not going to have enough pressure from the air to be able to expand your lungs. The water is going to keep your lungs compressed and you can't breathe. So if we increase that pressure to 4 atmospheres, now your oxygen pressure is 0.84 atmospheres. That's a significant elevation. Is it going to kill you? No. Is it good for you? Probably not. Nitrogen is also toxic at levels that are too high. If you look at the nitrogen pressure here, that's 3.12 atmospheres. Once you get around 4 atmospheres or higher, you can get nitrogen narcosis. It's sometimes called rapture of the deep. It has symptoms similar to alcohol intoxication. So you might say, well, that could be fun. But think about it. You know, you're 30, 40 meters below the surface of the water. Maybe we shouldn't have impaired judgment, right? Because something stupid there, you know, it's not like you're going to just, you know, trip and fall and hit your head or something. You could kill yourself. Yes?
So I have a question. So when you breathe, is it the lungs doing the work, or is it just the change of pressure?
That's a good question. When you breathe, is it your lungs doing the work, or is it the change of pressure? It's both.
Okay.
Your lungs are causing a difference in pressure. So when you inhale, you're expanding your lungs. That causes the pressure in your lungs to go down, and then air comes in from outside. You can only expand, you can only cause, let's start over. The pressure difference that you can achieve just with your muscles has a limit. Okay? And so if the pressure outside is far too great, then you're not going to be able to exhale. If it's too low, then you won't be able to inhale. And so there has to be balance. And that's why, you know, we need a certain amount of air pressure in order to be able to breathe. The thing that happens when you go below the surface of the air, it said every 10 meters is an increase of 1 atmosphere of pressure on your body outside your lungs because of the weight of the water, right? And so the farther down you go, the more pressure there is. And so if you're not breathing pressurized air, you're not going to be able to expand your lungs at all. I think it's pretty interesting. So a diver breathes a diver breathes a heliox mixture with an oxygen mole fraction of 0.050. Okay, what is heliox? Well, what if you want to dive really deep? How can you avoid getting too much nitrogen and too much oxygen? How about breathe something other than a nitrogen-oxygen mixture? So there are gas mixtures. Heliox is a mixture of helium and oxygen. When you inhale helium, what happens? Your voice changes. You sound like Mickey Mouse, right? But does the helium interact with your body? Is it absorbed? Does it do anything, really? No, it doesn't. The reason you can't just keep breathing helium out of the balloon is you'll suffocate because you're not getting any oxygen. But if we mix the helium with oxygen, we can use the helium to, in effect, cut the oxygen so that we can get the correct amount of oxygen. So my understanding is that if you're diving very deep, you're going to have 2 tanks, one of heliox and one of compressed air. And as you go deeper, you're gradually switching from the compressed air to the heliox so that you can keep your levels correct and not, you know, lose your mind and your life. So this particular heliox has a mole fraction of 0.05. So we could say chi O2 equals 0.050. No unit on that. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres, which is what your body would like to breathe? So we want the partial pressure of oxygen to be 0.21 atmospheres, same as standing on the beach. So we're looking for P total. Well, have we seen an equation that relates those? The P's and the chi. Yes, yes we did. PO2 equals the mole fraction times the total pressure. So I just need to rearrange that. If I divide both sides by the partial mole fraction of oxygen, these guys cancel out. The total pressure is the partial pressure of the oxygen divided by the mole fraction. So we want 0.21 atmospheres will be divided by 0.050. And my calculator gives me this number, 4.2 atmospheres. How many sig figs should that have? 2, and it does. That's nice. Any questions? So if you're down a little over 30 meters below the surface of the water, you're going to need a little over 4 atmospheres of pressure to breathe, and this heliox mixture would give you the right amount of oxygen. Pardon me?
Why do we use compressed air instead of normal?
Why do we use compressed air instead of just normal air? Well, when you go below the surface of the water, the pressure from the water is pushing on your lungs, and that makes it very difficult for you to expand your lungs. So if the air coming into your mouth or your nose has pressure on it, that helps you to expand your lungs. Good question. Any other questions? Doing experiments with gases is really awesome because we can figure out how many moles of a gas there are just by measuring pressure, volume, and temperature. But dealing with gases is difficult because they don't like to sit in beakers. They tend to escape. And so trapping them and holding them can be a bit of a difficulty. So we often collect gases by displacing water, using them to displace water. It's Monday. You collect the gas. I'm just going to jump ahead to the picture. So this is what we mean by collecting a gas over water. Here we have a chemical reaction. Zinc and hydrochloric acid generates hydrogen gas, which is going to build up a pressure and is going to try to leave the test tube. So we've got a tube through the hole in the stopper, and we allow the hydrogen gas to escape through the tube and come up into this inverted beaker of water. At the beginning of the experiment, this was completely full of water, kind of like a barometer. And then as the gas bubbles in, it displaces the water. So we're trapping the hydrogen gas. But this water is evaporating like water always does, and so we also have some water vapor, water in the gas state present in here, and so we've got a mixture. When you collect gas over water, you get the gas plus water. Well, the pressure of the water there depends only on the temperature of the situation. And so they've studied this, and there's tables, and you can just look up what the partial pressure of the water is. We call it the vapor pressure. So the vapor pressure of water can be found in tables like this. So if you're doing this at room temperature, 25 degrees C, the pressure from the water will be 23.78 millimeters of mercury. It's usually given in millimeters of mercury because that gives us more reasonable numbers than if we did it in atmospheres. All of these numbers would be really small. So if we want to know the amount of hydrogen, the moles of hydrogen here, this is like that pressure problem we just did, partial pressures. We have to find the pressure of just the hydrogen and then use the volume and the temperature to calculate the moles. So another example, a sample of acetylene is collected over water. The total gas pressure is 738 torr, and the volume is 523 milliliters. At the temperature of the gas, 23 degrees Celsius, the vapor pressure of water is 21 torr. So they saved us from having to go look that up. How many grams of acetylene are collected? Well, we want grams of acetylene. What is all of this gas stuff going to allow us to calculate? Number of moles. We can calculate moles of acetylene, right? So the first thing we want to do is use the ideal gas law to calculate the number of moles. And then we can use the molar mass to get the grams. So the total pressure, P total, equals 738 torr. The vapor pressure of water is 21 torr. What pressure do we want to use in the equation? We need the pressure of the acetylene. We don't care how many moles of water are in there. We don't care about the total number of moles. We want moles of acetylene, so we need to use pressure of acetylene. So if we subtract here, we get 717 torr, and that's the partial pressure of the acetylene. We're given a volume. The volume is I got ahead of myself, 523 milliliters. The temperature is 23 degrees Celsius. So we're going to use the ideal gas law. N equals PV over RT. What units do we need on pressure? ATM. So it's 1 ATM over 760. So 717 divided by 760. 0.94342 atmospheres. We need to convert milliliters to liters. So we want milliliters on the bottom, liters on the top. Milli means 10 to the minus 3. So that's 0.523 liters. And temperature, we need to convert this to Kelvin. Brain fart. 296.15. You like how the train makes the projector shake? It's not an earthquake. I grew up in Minnesota and Iowa where we have tornadoes frequently, and tornadoes sound like freight trains. Except they don't have sirens like that. Divided by R. Sorry, I'm spacing out. Liter, atmospheres, mole, Kelvin. And the temperature, 296.15 Kelvin. 0.94342 times 0.523 divided by 0.08206 divided by 296.15 equals. So the number of moles of acetylene equals 0.020303. And then we need to convert that to grams, which hopefully that's become fairly routine for you now. So grams per mole. We're given the formula there because I don't expect you to know that one. 12.01 times 2 plus 1.008 times 2, 26.036. Multiply that by the number of moles. And we get 0.52861 grams. or 0.529 grams of acetylene. Any questions? In problems like these, the issue is not solving the ideal gas law, it's getting all the numbers into the ideal gas law, identifying what they are. Two very common mistakes: students will use the total pressure instead of the pressure of the acetylene, very common. Forget to convert Celsius to Kelvin, or get this all written out correctly and then screw up talking to the calculator and end up with this huge number. Here's another one. So this was like the picture we saw earlier, the illustration of collecting a gas over water. Common way to make hydrogen gas in the laboratory is to place a metal such as zinc in hydrochloric acid. The hydrochloric acid reacts with the metal to produce hydrogen gas, which is then collected over water. So collected over water, important. Suppose a student carries out this reaction and collects a total of 154.4 milliliters of a gas at a pressure of 742 millimeters of mercury and a temperature of 25 degrees Celsius. What mass of hydrogen gas in milligrams does the student collect? Well, this is kind of like the last problem, right? They're asking for mass. They're giving us all this information about a gas. So we'll use the ideal gas law to calculate the number of moles, and then we'll use the molar mass to convert to grams, and then this time to milligrams as well. So for the ideal gas law, we need pressure, volume, and temperature. We're given a pressure of 742 millimeters of mercury. Is that the pressure we want to use in the equation? No, because that's the pressure of the hydrogen plus the water vapor. We need to subtract the pressure of the water vapor. What is it? It's not on the slide. You've got to go look it up. It said 25 degrees? Was it 25? Okay. So at 25 degrees is 23.78 millimeters of mercury. So we have to subtract the water vapor pressure. And we get 718.22 millimeters of mercury. And of course we have to convert that. Divide by 760. 0.94503. That's the pressure we want to use. Volume. The volume's given in milliliters. Here's another way to convert that. Instead of writing milliliter, write what milli means. Milli means times 10 to the minus third, and then liters. And that looks weird. It's not proper scientific notation, but your calculator will understand it. Or you can punch it into your calculator, and it will tell you that that's 0.1544 liters. And then we've got the temperature. Got to convert that to Kelvin. 25 degrees C. So that's going to be 298.15 Kelvin. I think we've got everything. So N is the pressure times the volume divided by R times the temperature. So there's my pressure times 0.1544 divided by 0.08206 divided by 298.15 equals 0.0059638 moles of hydrogen. Remember, hydrogen is a diatomic element. So its molar mass is 2.016 grams per mole. And then how do we convert to milligrams? Well, we want milligrams in the top, grams in the bottom. 1 milligram is 1 times 10 to the minus third grams. Okay, now you guys aren't paying attention. Yeah, so this is upside down, right? See that? It's easy to do, especially when you're scrolling across like this and you can't see where you've been. That's not a good excuse. So that one got upside down, so we need to... I realized as I was doing it on my calculator, like, wait a minute. And then this is messed up too, isn't it? No, it isn't. It's fine. I did that one fine. I messed up the other one. Okay. 0.0, no. Yes. 0.0059638 times 2.016 divided by 1 EE minus 3, getting 12.023, 12.0 milligrams. Any questions?
Do you expect us to memorize the different pressures of water vapor?
No, you are not expected to memorize vapor pressures of water. Like on an exam, it will either be given in the problem, that's the most likely thing, or you would be given a table along with the periodic table so that you could just look it up. Yeah, I don't know those off the top of my head. The only one I know is that the vapor pressure of water at 100 degrees Celsius is 1 atmosphere. Any other questions?